I was very pleased to come. Actually, for me, it's a relaxation. I just organized a conference that were about more than 300 people, and now I'm a guest, which is fantastic. And this is well-organized meeting, so I want to thank the organizer for inviting me. Okay, well, Doxil is rather quite a complex product. Today I'm going to talk about something much simpler, and I hope it will work well too. And this is a project that, how do I move the slides with this? Green. Oh. A project which is a collaboration, and it really deals with a field that's called tribology, which is the research or the science of friction. And this was done with a very well-known tribologist from the Technion that actually dealt with machines. And together we tried to deal with the problem of lubrication in the joints. So this was already talked, I'm going to skip it, but basically the major issue is osteoarthritis. And what we can see here, there are different ways of treatment. You can deal with corticosteroid by oral administration, which reduce inflammation. That's a later stage of the disease. Or a very common treatment today is hyaluronic acid, which really people claim it works with the viscosity. There is no battery here. Or you can work, which I show you, with liposome, which deal with the boundary lubrication. Now, as we can see, this is a major disease of everyone as long as you get to an old age. And you can see a number, I don't want to deal with it more. And that's the treatment I told you. Hyaluronic acid actually is the only treatment today which really helps at the early stages of the disease. It's considered a medical device because it's just acting physically. It doesn't involve any kind of metabolism or any similar effect. The problem with it is it's very short lasting. So hyaluronic acid will disappear from the side. We measured another by different method in about 8 hours. So the effect is very short lasting. And that's of course a problem. Still the market is extremely well. Altogether now all over the world is exceeding $1 billion. Now, we decided to use liposome. The reason actually started from a study by Hills, an Australian scientist. Unfortunately, he died in the middle of a clinical trial. That he used a lipid that he injected in a propylene glycol to the joint intra-articularly. And he based it on, he's a biologist, so he based his study on the fact that osteoarthritis at the area of damage, there is less phospholipid, and he claimed that the phospholipid are part of the lubrication mechanism. This was published. He went to do a clinical trial with quite encouraging results, but unfortunately he died. He used a DPPC in propylene glycol. He died, and because of argument between all the people in the group, this study was not continued, unfortunately. So we learned about it, and actually we are a team of people. And one of us pointed to the use of this lipid, and I decided to go into it and to search which lipid to use. Well, the cartilage is very fascinating by its structure. It's actually an hydrogel by definition. It has a layer on the top. You can see it has the collagen fiber that really are embedded into a hydrogel of proteoglycans. So it's rather interesting structure even to material sciences. And it really built to last tremendous wear. You can just see how long we work, and still the collagen really retain its strength and its ability to protect us against all these bad things that we discussed before. Now, how to use the liposomes? We can see it doesn't work anyway, so it's okay. I'm sorry, but you can see the important part of it is the synovial fluid, which actually is between the two layers of cartilage. And in these fluids, there are some lubricants, natural lubricants, protein and lipid that are protect us. And when we want to treat, we actually inject into this region. It is important to say that there is a membrane coating this area which has pores that are about 200 nanometers in size, and I want you to remember it. Okay, now when we decided to design it and use the same approach we used during the development of Doxil and other, which when we look what performance we want, what kind of things we needed, and we discussed it already, what are the properties in terms of what lipid composition, what are the size, lamellarity, all these properties, and based on this, we actually planned the method of preparation and the processing and fabrication of our preparation. I don't think I have to say much about liposome, but I have to say that it is very versatile, and I especially put only two kinds of liposome, the multilamellars and the small unilamellar. The small is extreme in this case, 20 nanometer, and the large can be a micrometer size. Actually, we have a huge number of types of liposomes, but all of them share some common, very good from our perspective properties. They are biocompatible, biodegradable, they are not immunogenic, they're familiar to the scientific community, have known pharmacokinetic and biodistribution, known metabolism, and therefore their toxicology is really much better than most other nanoparticles we have today. They have a phase diagram well known, and it was interesting to us to study which part of this complex phase diagram proposed by Moritzen in Denmark and his team is really relevant to us. And we found a liquid disorder in which there are high flexibility, high compressibility, and high level of hydration is the best of all the phases that we see here. So we look at this lipid, and then by definition, from what I told you before, the best one are the lipids that have phase transition in the range that we want. DMPC, phase transition 22.3 degrees. DPPC is already too high for us, but if we mix DMPC and DPPC, we'll get a good combination. But we tested all of them. All the composition that are here are tested, and that's actually a proof, confirm our first assumption that the liquid in the liquid disorder quite close to the phase transition are the best. These are the many kinds of liposome. We compared all of them and found, for reasons that I show you in a minute, that the multilamellar liposomes are the best. We checked which method we are going to use. Actually, people involved in the field know that all animal models are really very poor. They don't really imitate the human osteoarthritis at all. And the other things we wanted very much to do is to find some physical-chemical approaches by which we can calibrate the system and make prediction. And we found that a parameter called compressibility, which we measure by using different, mainly ultrasound technology, I don't have time to go into it, is the best because it's determined the property that are very relevant for our physical property that we need to put for the application and prevention of wear. This is described in two papers, you can find them here. Show you that MLV are the best. We took a piece of human cartilage and tested how deep liposome will go inside it, applied pressure in a similar mechanism imitating actually what happened in the joint, and you can see very clearly that the DMPC MLV remain on the top, while SUV go deep inside, and that's really related to the porous structure of the cartilage that I showed you before. So actually this told us that DMPC will be the best, which indeed is the case. That's the way we work. We get some part from the hospital with all the permission, not very easy to get, of the cartilage. We take disc out of it, so we really have the surface as we want. We can use the disc at any level we want, with any size. We put them in, and this we do for the wear study. For the wear, we also take part of the bone. We have a device, it's called a tribometer actually, the machine, in which you have one moving part and one static part, and there are two discs attached to them, and now you can move them in any medium you want for any length of time you want. And actually with this you can study both wear and friction, effect on the friction coefficient. And this actually, you see the description of the instrument, you can look at the reference, you can do it any temperature you want, so the conditions are well controlled, and it is based on human, and on a friction between two human cartilage pieces, which is what you get. That actually show you one experiment in which we measure friction. You can see there is one static, one moving, and we can measure the friction that's really in different media, and we get two values, one of the static friction and the other of the dynamic friction upon motion that you can then tabulate and see the effects. What you can see here very clearly, this is the data that again DMPC MLV and DPPC MLV are the best in terms of reducing the friction as the best lubricant that we have. And the others, you can see also effect of synovial fluids and other DMPC SUV, the same composition, work very poorly because the reason that I told you that actually the liposomes are not staying on the surface. We can imitate hiking up to 100 kilometers. I'll show you data about imitating hiking of 50 kilometers on the wear. And you can see we tested two parameters which are the best. One is actually wear that we measure by the amount of collagen that remove into the medium, and also the proteoglycan, which has a much better baseline. Actually, what you can see that first of all, it's amazing how strong the collagen, because the amount you get is much less than 1%. So, but still, in a minute you can see very large difference. Again, we compare the same liposome, all are MLV in this case, and you can see here, you also have study with the hyaluronic acid that you can see, and you can see here that the MPC, DPPC liposomes are the best. Second are the DMPC, and other are much worse. Actually, if you take inflamed synovial fluid, ISF, from a patient that have inflammation, you can see that if you add the DMPC, DPPC, you improve the lubrication and reduce the wear quite dramatically. So basically, these are the conclusion that we have the DMPC, DPPC liposome and DMPC as really a good reducer of friction and a good reducer of the wear. And the other thing that we demonstrated is that it stays on the site for a very long time. So one injection can keep it for 1 month there. I'll show you the results. And actually, we also did some toxicology in animals, showed that they are really totally naive. There is no any toxic effect that we can measure. If we use other liposome with DMPG or other, we start getting really accumulation of macrophages and a lot of things that are unwanted. So what is the mechanism? And by this I'm going to end. The mechanism is that we thought about two options. The first one is that the liposome will attach to the surface, and they do. You can see them there very nicely. And because of the pressure and the friction, they will delaminate. You find the lamella, and the rest of the liposome will remain as a reservoir. And then there are two options. The first is the common mechanism that all should know from your cars, that you have hydrophobic lubrication, namely because of the oil. You look at the friction of the plane and you can see that it should move smoothly. But that's not the case for many reasons. One of them, thermodynamic, it's exposure of hydrophobic region to the water. This is unallowed. It cannot happen. So we have to go to the second mechanism, and this is that actually you have two bilayers that will form on each of the opposing cartilage pieces. And you see the friction plane now. Every head group of phospholipid here, a lot of water attached to it, and the water actually acts as a nanoball bearing, allowed a very smooth lubrication. This mechanism was proposed some years ago by other system, by Jacob Klein from the Weizmann Institute, one of the best tribologists in the world today, and we really adapted this mechanism. Now we are working with him. He got so excited about it that now we have very basic project. We got ERC together on this project to deal with the really most scientific aspect of this. So, as I told you, we are going for a medical device. You can see here that liposome, the lipids with radioactive lipids stay very long attached to the cartilage. Very little goes to other places, and if they go to the liver, of course, they will metabolize because they are regular lipids. They are nothing fancy about them. I'm going to skip toxicology. These are the two, my collaborators. You can see a group of students and people from our lab, but the main one is actually Professor Etzion, the tribologist, and I think I want to thank you very much.